Hey guys, it's Tay, and today we're going to be going over the Unit 2 MCQ. Alright, so to start off with, question number 1. Oh, there's a little mark here. Okay. 3 boxes are pulled to the left by strings with negligible mass on a horizontal surface as shown above. The masses of the box are M1, M2, and M3, where M3 is greater than M2, which is greater than M1. Friction between the boxes and the surface is negligible. The figure below shows the force diagram for each box. And so the question asks, given that M3 is greater than M2, which is also greater than M1, how do the force F and the string tensions TA and TB compare? Okay, so the first thing to note is what each of the forces contain. So let's start with TB. TB is only a combination of M3, right? If you were to pull TB, so pretend that this block right here was not there. If you were to pull only TB, only M3 would move. So TB consists of M3. And now TA. So if you were to remove this block this block right here, and you were to pull right here at the tip of the string, it would be moving the mass M2 and M1. And so TA equals to M2 plus M3. And if you were to pull the force F is equal to M1 plus M2 plus M3. Thus, F will be greater than TA, which will be greater than TB. And so if we look over here, that is our final answer. It just says it backwards, but it means the exact same thing. Alright, question 2. So these questions are continuations of each other. So it says, which of the following is a correct ranking of normal forces F1, F normal 1, F normal 2, and F normal 3. Sorry, it's a bit hard to read on the boxes. So the first thing to note is what the normal force consists of. So the normal force is just equal to, so it's equivalent to the weight force. So the weight force has to be equal to the normal force according to the free body diagrams shown here, since they are equal in length or magnitude. So the normal force is basically the weight force. And so we know that weight is equal to mass times gravity, which is 9.81. And so what we can do is, since G is constant, and we know weight is equal to the normal force, so that means M has to be the only factor that affects it. So if M3 is greater, that means the normal force of, mass 3 will be greater. And so basically in this order, we could just write it as FM3, FM2, FM1. And so our answer will be C. Alright, so let's look at this problem. So a student is trying to determine the tensions in the string connecting the boxes. If the acceleration of the system and the pulling force F are known, which of the following pairs of equations could be used to find the tensions? So I know that this is a little bit hard to read, but all of these signs are equal signs. Equals to, that's a minus. This is an equal sign, that's a minus. This is an equal sign, that's an equal sign, that's a minus. That is an equal sign. So it's a little bit hard to read, but yeah. Okay, so which of the following pairs of equations should be known? So this is a very weird problem because in a way you don't know how to approach it at first. So first thing we could do is look at F. So F will be a combination of M1 A1. Using Newton's second law, we can set it equal to MA. So we have M1 A1 plus M2 A2 plus M3 A2 A3. Okay, and so let's look at what else we know. So we know TB. So TB, since it's as we discussed above, only affected by this box, we can set it equal to M3 A3. And TA will be equal to M2 A2 plus M3 A3. Okay. So we know that the force F would then be equal to M1 A1 plus tension in A. And so if we look at our equations, we see that, here, let me use a different color. I'm going to underline the ones that are right. We see that this equation is valid. But now that we know what F can be equal to, so basically it crosses, it takes out this one since that one's obviously wrong. And even though this one is correct, it is still wrong. The whole answer choice is still wrong since it's asking for the pair of equations that can be right. Let's go ahead and take a look at the other two. So while looking at the answer choices, we see that it looks like they have manipulated some of the expressions to look a little bit different. So we can say that this is the same thing as M2A2 plus TB. Okay? And which is also the same thing as TA minus TB equals to M2A2 or M2A2 equals to TA minus TB. And so if we look at our answer choices, we immediately find that, let me change the color back. This is our equation of what M2A2 equals to. And we know that since that's what M2A2 equals to, we know that this one would be wrong, making this answer choice completely wrong. We know that this would be wrong, making this answer choice completely wrong. And so we know that this is a valid solution, and we already proved that TB is equal to M3A3, which is right here. So that's why B is our only answer choice. All right. Students attach a force probe in the middle of string A to measure tension A, then use a different force probe to provide the applied force of the box mass M1. With the box of mass M3 held in place by one student, a second student posed to the left on the force probe that provides the applied force F. As the student posed the steady force and with the boxes remaining at rest, the following pairs of readings from the two force probes are recorded at different times. So let's take a look at our data. What is our data saying? Okay, so over here is the total force. Over here is the tension force in part A, which includes M2A3 or A2 plus M3A3. That's what TA is equal to. And the force will be equal to M1A1 plus TA. So based on the measurements above, how do the magnitudes of the two forces of quantity compare? Okay. So this says time 1, time 2, time 3, time 4, time 5. Sorry, it's a bit blurry. So we have 10.6, 10.4, 10.2, 10.8, 10.6, 11, 10, 10, 11, 11. Okay. So these values are very close to each other. The closest being like 0.6 newtons apart, the smallest being 0.6 newtons apart. But let's see what this is saying. So based on the measurements above, how did the magnitude of the two forces compare? So they agree numerically. Well, obviously not. They're not the same at all. The two quantities disagree by an amount that is larger than the experimental uncertainty. Well, the experimental uncertainty should be the greatest distance between the one that's wrong. So between, let's see, here, 0.8 newtons. So, yeah, obviously that's not right because, the number is not so large. The numbers are fairly close to each other, so it's not that they disagree by a larger amount. An example of a larger amount would be 14, for example. If TA was 14, then option C probably would have been right, but it's not. The two quantities cannot be compared because the force probes have different level of precision. Well, I mean, it doesn't state that they use a different type of force probe. They just say force probe, so you can assume they're the same. The two quantities agree with an experimental uncertainty, but do not agree numerically. So, numerically, they're not the same, so of course that part's right. And they agree with an experimental certainty because the numbers are very close to each other, so that's why option B will be correct. Alright. A motorized cart is attached to a string that passes over a pulley. The other end of the string is attached to a hanging block. In the figure shown above, the car is accelerating to the right. Which of the following best represents the forces acting on the cart as shown? So, the first thing to note is that the cart is accelerating to the right. What this tells us is that the vertical forces in the vertical component, must be equal to 0. So they must be even. So we can do our first test along the answer choices and see that this is even, so we leave this as a maybe. This is not even. The force normal and the force gravity are not even, so we can cross out answer choice B. These are even. These are not even, so we can cross out those. Next thing to note in the sentence is that it's accelerating to the right, meaning that the force applied has to be greater than the tension force. Otherwise, the tension force would be pulling it to the left. So, in answer choice A, the tension force is greater than the applied force, so that would imply that it's moving to the left. Thus, A is wrong. So, that leaves our only answer choice as C, and we can see that the applied force is greater, so our answer choice is C. Alright. Oh, this is a duplicated question. Okay. A hockey player uses a hockey stick to hit a puck such that the stick provides an applied force on the puck. The puck travels for a distance of 0.85 meters while experiencing the force from the stick. The puck leaves with a speed of 8 meters per second and travels at a constant speed in a straight line along a horizontal ice up for a distance of 12 meters. The frictional force between the puck and the surface is negligible. How does the magnitude of the force exerted on the puck compare to the magnitude of the force exerted on this by the puck on the stick at the time interval in which the stick is in contact to the puck? Okay, so College Board questions are really, really wordy, and so let's just break down the information that we know. So we know it travels for a distance of 0.85 meters, and we won't know if we'll need this given data, but it's nice to underline what you know. It leaves at a speed of 8 meters per second and travels at a constant speed in a straight line for a distance of 12 meters. So since the friction in the puck, or friction force between the puck and the ice is negligible, so friction is negligible. So how does the magnitude of the force exerted on the puck? Okay, so essentially since friction is negligible, that means that the puck will not slow down, it will keep going. And so what we can note by Newton's third law, action-reaction pair, is that they should be equal to each other. This is the only option that makes sense. Alright. A hockey player uses a hockey stick. Okay, same thing. Which of the following statements best describe the force or forces exerted on the puck after it is hit by the stick and slides on the ice? So the applied force from the stick is still exerted on the puck during this time. Well, I mean, it says after it is hit. So the applied force from the stick is no longer there. It's gone. Since the puck's acceleration is 0, there are no forces exerted on the puck during this time. Well, it does say that it travels at a constant speed. So when you have a constant speed, you can think of it like constant velocity, although the direction may be changing. So this means that the velocity on a velocity time graph will be 0. And that also means that the acceleration will also be 0 since the velocity is 0. So yes, this part is true, but it says that there are no forces exerted on the puck during this time. The thing is, the question never states that the puck is massless or the puck's mass is negligible. It only says that the frictional force is negligible. So that still means that there is a weight force and there is a normal force. Thus, there are forces still exerted on the puck during this time. So, although the first part is true, the second part isn't, which makes the thing false. Since there is no frictional force exerted on the puck, a normal force is not exerted on the puck, but the gravitational force is exerted on the puck. What this means is that since there is no normal force, it would keep going down. Thus, this one's wrong. I mean, it doesn't make sense, right? That would mean that the change in the forces of y would be equal to 0, or would not be equal to 0. So that's obviously not right. There is no frictional force exerted on the puck, and the gravitational force and normal force exerted on the puck are equal in magnitude. That's exactly what our question states. It doesn't state that it's changing in y. Thus, D is our answer choice. Alright, next question. A block slides down with constant velocity down an inclined plane that makes an angle theta with the horizontal. It experiences 3 forces: a gravitational force, a normal force, and a frictional force. Which of the following gives the magnitude of the net force on the block? Okay, net force. So that's telling us force is equal to mass times acceleration. This is what that part of the equation is telling us, or question telling us. This is telling us that it's constant velocity, which, if your velocity is constant, that means there's no change in acceleration. That means that the acceleration is just equal to 0. So that means that if we plug it into our equation, 0 times the mass, or 0 times anything, is just equal to 0. So this will just be equal to 0. Thus, A is our answer choice. So a lot of times people make the mistake where they just go ahead and try to solve or try to understand why these answer choices are there, but they don't look at what's given to them, or they don't read the question carefully enough, so they don't see that the question already tells you what the answer is. You just have to plug it in and see. So all of these are out. Alright. In the setup shown in the figure, 2 blocks of equal mass m are at rest, but are just about to slip. Also shown is a free body diagram for the block on top of the table. In this setup, the coefficient of static friction between the table and the block resting upon it must be... Okay, first thing to note is that it's resting. It's at rest right now. It says it's about to slip. That's not important. It's at rest. And so since it's at rest, we have this free body diagram. And so the tension force must be equal to the frictional force. So UMG must be equal to the frictional force. Oh, I just did the frictional force on the opposite side. Must be equal to MA. So we can cancel out this, and we know in order for these to be equal to each other, since this equation is equal to each other, that means that the coefficient of kinetic friction must be 1, at least 1, in order for G to be equal to A. It obviously can't be 0, because if it was 0, that means that there's no friction at all, but the problem says that there is friction. If it's between 0 and 0.5, that means that the block is no longer at rest, it is moving, since the tension force would exceed the threshold. If it's between 0.5 and 1, that still means that the tension force can exceed the threshold of the box. But if it's at least 1 or greater, that means that the this box right here can't move at all. Alright, three blocks with mass M1, M2, and M3 are attached by strings, as shown in the figure above. The coefficient of friction between each of the blocks and the horizontal surface is U. The tension in the left and right string T1 and T2 respectively. If the acceleration of the block is A, which of the following expressions is equal to T2? So, for these kind of problems, it's kind of difficult to start without noting what you have. So we know that T2 will be equal to M3A, and since they all have the same amount of friction between them, A should be the same between them. It is safe to assume that they are the same. Okay, and so we have T2 is equal to M3A minus the friction force, so we get the total net force, minus U times the mass times the gravitational pull, since it's the normal force, but normal force equals to weight, and we can just put gravity as that. So this will be what T2 is equal to. Now T1 is equal to M2A minus the coefficient of kinetic friction, M2G, plus M3A minus UM3G. And so what this tells us is that we can substitute this into this equation, and so we get that T1, or actually no, we know that T1 is equal to M2A minus UM2G, which is also equal to T2. This is an alternative form. And so what we can do is we can substitute this into here, and we get that T1 minus M2A minus UM2G would be equal to T2. And the math checks out, so option B will be our final answer. Question number 11. A falling skydiver opens his parachute. A short time later, the weight of the skydiver parachute system and the drag force exerted on the system are equal in magnitude. Which of the following statements predicts the motion of the skydiver at this time? So, the first thing that we can note is that the drag force on the system and the weight are equal in magnitude. This tells us that the skydiver parachute system has reached terminal velocity. And so this obviously means that the skydiver isn't at rest, he's falling down. He is moving downward, so we can keep all of these parts. Okay, so since he's in terminal velocity, that means that the net force is 0, right? So if the net force is 0, that means that there's no acceleration. So we can cross out C, we can cross out B, and constant speed basically means that there is no acceleration since the rate of change is constant. Thus, there's no change to be noted. Alright, the following figures each show vectors representing the forces of an object that is initially at rest. In which case will the object remain at rest? So, for this one, the horizontal components are equal, but the vertical components are, so it's not at rest. For this one, their horizontal components are not equal, so we can cross that out. For this one, okay. So the first thing we want to do is note that the sum of these two forces is equal to this one. And so it's equal to this one plus the force that's already pre-existingly there. So it's just basically, if this is, let's say, length, and that's length, the total is 2 length, okay? And this one looks like it's twice the length, too. So it's safe to assume that because using vector addition they're equal, that this one will be equal. But let's take a look at our final answer choice. So for this one, we know that adding this vector plus this vector would yield this vector. But the problem arises right here. So when we add them, let's just say that this is 90 degrees. Let's say that this is 30 degrees. Let's say that this is 60 degrees. So if we bring angles into this, obviously this base right here will be shorter than this length right here. And so it's not safe to assume that because that is shorter, that these two are equal. This vector is equal to this vector, as you see underlined. And so because of that, the resulting force would be going to the left. Thus, this is not equal. This is why answer choice C is correct. Oh wow, for question 13, no answer choices showed up. Let me go ahead and write them down. Oh no, they're just on the right. Okay, my bad. Okay, a person kicks a ball into the air with force F. The figure shows the position of the ball at various times. What is the net force on the ball and its acceleration at the highest point shown? So the first thing to note, the answer choice is wrong for this one, and I'll explain why. The first thing to note is that since the ball is into the air, we will always be having a force of acceleration on it that is pointing downwards at negative 9.8 meters per second squared. And so because it is falling, because it's going up and falling, that means that the net force can't be equal to 0. So and the acceleration is obviously not 0, it's negative 9.8. So this is wrong. So this is A, which is also equal to G. So we know that the acceleration of these two are correct. And so this one's wrong, so we can cancel this one out. And so between choice B and C. So now let's look at the force. The force is equal to MA, and since A is equal to G, the force is equal to mg. Thus, this is correct. This is basically saying 2F, which is not correct. So answer choice B is our answer. Alright. Two astronauts of identical mass are connected by a taut, is that what it says? Taut cable of negligible mass, as shown in the figure above, and are initially at rest with respect to a nearby space station. Astronaut Y pulls on the cable towards herself with considerable force. Which of the following describes the direction of the velocity of the center of mass of the two astronauts after astronaut Y pulls on the cable? So the first thing to imagine is that you're in space. So if you pull this way, or if you pull this way, you're going to bring yourself closer to astronaut X. And if astronaut X is just standing there, astronaut X is going to be pulled towards you. And so since you're just moving together, the center of mass stays in the middle, so it does not really move at all. Alright, next question. Two blocks of mass, 2 kilograms and 3 kilograms are connected by a lightweight or a light string that passes over a pulley as shown above. The pulley has negligible mass and friction. The two-block system is released from rest. Which of the following correctly describes the velocity of the two-block system's center of mass? Alright, so the first thing to look at is which one is heavier. So it's released from rest. So obviously it will be moving this way. This block will be moving this way. So the center of mass should be in the middle, so we can assume it's like right there, okay? So after it's released from rest, the center of mass is going to move in this motion. So it's going to be moving, it's essentially going a little bit upward, but it's mostly moving downward. So we can already cross out these two answer choices. And since it's moving downwards, it will also start to increase speed until it hits the ground. And so that means that the if it's increasing speed and staying in the same direction here, that means the velocity is also increasing. And so our answer choice is C. And this would be wrong because it says decreasing. Alright. Two ice skaters, skater X and skater Y, are at rest on a horizontal surface made of ice. The friction between the ice and the skaters is negligible. Skater X, who has a smaller mass than skater Y, pushes skater Y such that skater Y travels at a speed of 2v to the right. Which of the following indicates the direction of the velocity of skater X and the direction of the velocity from the center of mass of the two-skater system after the push? Alright, so the first thing to note is that skater X is lighter, so X is mass is less than Y's mass, okay? So let's say you have a really heavy 2-ton block for some reason. Now let's say that you jump up like while you're in air and you try to push this 2-ton block. So I'll draw a little guy right here, he's in air. We draw the floor, okay, and he's trying to push this block, but he can't. What ends up happening is the block pushes him back and he moves to the left. That is essentially the exact same thing that's happening. So the skater X's velocity, so we can pretend that since it's heavier, we can pretend that this is skater Y. And so skater X would be moving to the left. Now the center of mass, it doesn't say that skater X falls or moves to, or falls on the left side or falls on the right side or starts floating or something like that. So the center of mass just remains the same. It just stays 0 since there's no change in it. So our answer choice B is our answer. An object of mass m is dropped near the surface of Earth such that the gravitational field provides a constant downward force on the object. Which of the following describes what happens to the center of mass of the object Earth system as the object falls downwards towards the Earth? Well, I mean, think about it. If you're flying on an airplane and you drop, pretend like there's no wind or anything, that there's only one force, and that's the gravitational force. If you went up into the sky and you just drop something straight down, it would just fall in a straight line. So it doesn't move towards the center of the Earth because you could be at the edge and it still fall down. It moves towards the object. I don't even know what that means, so this is obviously wrong. The answer cannot, no, it can be determined. It just does not move. It just falls straight down. Oh joy. Okay. Question 18. 3 blocks are sliding together to the right along a surface of negligible friction when a force with magnitude F external is exerted to the left on the rightmost block as shown in the figure. The masses of the block are indicated in the figure. If the force is exerted for a time delta t, what is the change in velocity of the systems of the center of mass of the 3-block system? Wow, I've reached that stage where I'm just doing so much math and reviewing physics that I forgot English. Okay, that's not the point, but okay. So for this problem, the first thing we want to do is note that we have a delta t here. We're talking about a force, so the force external obviously has to be equal to ma. Okay, so that will be equal to, okay. So how the hell did we get something with delta t in it? Well, I mean, let's look at what we know about each of the quantities. So for mass, there's not too much to mass. We know mass is a part of weight and stuff. But for acceleration, acceleration is defined as the rate at which the velocity changes. And so we know that acceleration is also equal to delta v over delta t. And so the force external equals to delta v over delta t times the mass. But it's not what we're looking for. We're looking for the change in velocity of the system's center of mass. The change in velocity, well, I mean, now that we have this equation, we can just rearrange it. So we get, my bad, I forgot. The mass is equal to 6m, because you just add these. That's a total of 6m. Yeah, maybe that's not the best way to denote it. So let me just put 6m right there. And so we can solve for just the velocity by isolating it. So we got force external times delta t divided by 6m is equal to the change in velocity. And so our final answer should be A. So this problem is a little bit confusing, but if you're stuck on a problem and you only know how to get to this step, see what you know about the variables. It can help you determine a lot. Alright, next question. Block A of mass 4m is attached by a light string to block B of mass 2m. The string passes over a pulley with negligible friction and negligible mass. Block A is held a distance h above the ground as shown. The blocks are released from rest, and block A reaches the ground 2 seconds later. The value of h is most nearly. Okay, so let's look at what we know from the diagram. So we know that the net force is equal to, F equals to ma, net force is equal to ma. Well, in this case, we know that the net force will be equal to 2 times the mass, and since there's negligible friction, the only acceleration we worry about is g, so 9.8 or negative 9.8, so g. G is also equal to A in this case, so we can say the net force is equal to 2mg. And we know that the mass of the system as a whole is 6m since we're not including the rope. So using Newton's second law, we can set 2mg equals to 6m. And we can solve our 6ma. So this is the total mass. This is minus 6ma. And so what we end up getting is well, we can simplify this into 3. You can simplify this into 1. 1/3 g is equal to the acceleration. Okay. So now that we know what the acceleration is, we know what the mass is, we know what the time is. So the time is 2 seconds later. Let's take a look at our knowns. So we have v initial must be equal to 0 meters per second. We know that the total time is 2 seconds. We know that the acceleration is equal to 1/3 g. And so with this, we can use our kinematic equation delta x. So the change in x is equal to v initial times time plus 1/2 a t squared. And so plugging the values in, we get 1/2 times 1/3 times 10 times 2 squared is equal to 1/6 times 10 times 4. And so we get 1/6 times 40, and that should be equal to around 6.7. Thus, 6.7 will be our answer. Alright, next question. A 1 kilogram block is placed near the top of an inclined plane at an angle of 30 degrees with respect to the ground as shown by B. By correctly determining the effects of gravity, a student predicts that the acceleration of the block will be 5 meters per second. After allowing the block to slide on an inclined plane, the student finds that the acceleration is actually 4 meters per second squared. What type of force did the student most likely not account for when predicting the acceleration of the block? And what is the magnitude of that force? Alright, this is an interesting problem. So he is off by 1 unit of acceleration. And so really looking at this problem, he definitely accounted for the weight force since these are equal, so they must be 0. He definitely accounted for it going this way. So that leaves that the only force that he forgot to really apply was this force, which is the frictional force. And since he's 1 meter per second short, that means that he forgot to do 1 newton of the force of friction. And the math checks out. If you want to set up the equations and set them equal to each other, go for it. Alright, last question. A 3 kilogram block or 3 kilogram object experiences a rightward horizontal acceleration of 6 meters per second squared as it slides to the right across a rough horizontal surface. The table contains the label and magnitude of 4 forces exerted to the right or left on the object that represents measurements from an experiment as the object accelerates. Which pair of opposing forces in which directions could be responsible for the acceleration of the object? Alright, so it's a 3 kilogram object and a horizontal acceleration of 6 meters per second. We can tell that the net force should be equal to 3 times 6. Net force will be equal to 18 newtons. Okay? And so now it's saying which pair of opposing forces in which direction could be responsible for the acceleration of the object. Well, that's telling us if the two forces are going in opposite directions, that means you have to subtract them. So now the question is saying subtracting which two forces is equal to 18 newtons. So force 1 and force 2 results in 24 newtons, which is not equal to 18, so it's not A. Force 3 and force 2. So the magnitude of that, so the magnitude of 6 minus 24 is equal to 18. So that is correct, but we can continue checking. Force 4 and force 1. Well, 30 minus 30 is obviously 0, so no. And force 4 and force 3 is equal to 6. And so that is wrong. So that leaves our only answer choice being B. Well, I hope this clarifies any questions you have, and if you have any more questions, feel free to DM me on Instagram or leave a comment down below. I hope you enjoyed this video, and I hope I'll have time to make more for the other units. Bye-bye.